Hi everyone, I'm Chris Saxon. I'm part of Stephen Feuerstein's Oracle Developer Advocate team and part of the Ants team on AskTOM. It's my job to help you get the best out of Oracle database and hopefully have a little bit of fun whilst doing so. So with that in mind, we've got these office hour sessions, chance for you to discuss SQL issues with us and put some problems to us that you've been struggling with. We have a focus topic usually. This time we'll be talking about how joins actually work. We are going to be talking about how joins work in SQL this time around. So we've got some demos, some examples, and I'll be working through how the three different join types actually work. So let's go back over to here. Let's see. So hopefully we've got my screen up again. And okie dokie. So let's say, as I said, we're going to be discussing joins. So we've got the three different key join types in SQL. So nested loops, hash joins, and merge joins. And what we'll be talking about is the difference between them, how they actually work in practice, what the process is that databases follow to implement these join types, and their relative strengths and weaknesses. So what we'll be doing is I will be doing a bunch of demos and some examples as well. So we'll start off with some unindexed joins. As I say, I'll go straight into the demo. So hopefully now you can see my SQL developer screen where I've got a deck of cards, and you can see there's just things, various cards, suits, and values. And we just do a little info on those to take a look. You'll see all the various values in those. This will take a second or so to run. And there we go. So we can see the columns, the high values and low values. So if you're not familiar with the info or info plus command, it's like a better version of describe. Gives us some stats as well as what the cards are, or the columns are, and any indexes that are on those columns too. So we can see we've only got one index here on this damaged column. So what I'm going to do is join these two, join the table to itself. Bit slightly strange join, but there we go. I'll just check that the suit and value equals itself. Just doing this to keep things nice and simple and fairly straightforward. There are no indexes on any of the columns in the join here. So time for a little question for the audience and see who can predict what kind of join we're going to get here. So when I run this query, when I do the auto trace and look at the plan, what kind of join are we going to get here? Are we going to get a hash join, nested loop, or merge join? And just if you could put your comments in chat or your predictions in chat, and then I'll run it in a second and see what we actually get. So hang on. Okay, so let's see. Oh, one going for nested loops. Any other takers? Hash? Any other vote? Any other vote before we go ahead and do this? So everyone else is sitting on the fence, not wanting to go things. Oh, we're 50-50 nested loops and hash. 50-50. Let's have a look and see. So let's get the plan, the auto trace, see what the query actually does when it runs. So that will run away and give it a second to come up. So let's see. So up, we have got a hash join. So what it has done is combined all the two tables using a hash join. Hey, well done, Neil. Yes, well done, yay. So why has it chosen a hash join? Well, a hash join runs through all the rows in the first table, building the hash table, then probes it using the second table. I've got some slides showing more detail exactly how this works. But generally speaking, a hash join is the fastest way when you're joining all the rows in a table, in two tables together like this, on equality. So, and most joins are like this. You're checking that values from one table equal values from another table. Let's do something a little bit more unusual. So let's just save that, pin it there. I'm going to look for all the rows in the first table where the suit and the value is less than the suit and the value in the other table. So I'm not checking where they're equal, I'm checking where they are less than. And so guesses, predictions. What join type are we going to get here? Nested loop, hash join, or merge join? Let's see any more guesses, predictions about what we might get here. Okay. And merge from Neil. No, question mark. You're not very sure about that. Any other takers? Any other guesses? Nested loop from Amir. Not at all sure from Neil. Okay, yeah, fair enough. You know, it's this type of query, or this type of join, I should say, is pretty unusual. It's very rare I recall actually seeing one or writing one where you do something like this. So I wouldn't be surprised that people don't really know. Anyone else going to have a guess before we see what actually happens here? Doesn't seem there's any other takers. Okay, let's try again. And here we go. Bring it up. And, oh, there we go. We've got, well done, Neil. We've got a merge join, as predicted. You're not quite sure how you managed that? All right. So as you can see with the merge join, if I can just make things a bit bigger here and get rid of that, what it's doing, it's sorting rows in the first table and the second table. So it sorts both the data sets before joining them. And when we're doing a comparison like this, you know, greater than, less than, and so on, this is something that actually makes sense because it makes it efficient to walk through, I should say, sorted data sets. You know, it's quite easy to find all the rows that are less than a particular value if it's sorted. We can just walk through the ordered data set until we hit row that's not less than the value we've got at the moment. Again, I will show you in more detail how this works in a minute. So let's just pin that one. So that's less than. So let's do something probably even more crazy. Let's look for rows where they are not equal. So the suit and value are completely different. So neither of them are equal at all. Okay, so guesses, predictions this time. What are we going to go for? Nested loop, hash join, merge join. Any takers for what we're going to do here? People thinking away. Another merge from Neil. Any other guesses? Anyone? Any other takers about what we want to do? Hash again from Gilliam. No. Any other predictions before we run it? So let's try. Oh, anti-hash join. Ooh, interesting. Interesting suggestion. Okay, let's run this. We'll get the plan up again. So we've got a few different predictions, and this time, nested loops. So it's with a nested loop, what it's doing is reading every row in the first table, and then for each of those is doing a lookup of the second table where the values are not equal to each other. And this sounds like quite a crazy thing to do, because if you look, we've got two full scans here. And if we look at the second full scan of the inner table, we actually do that 52 times. So this starts column, I'll bring this starts over here, makes it a bit easier to see. So we read the first table once, get 52 rows out of it, the cardinality, and then for each of those rows, full scan that inner table 52 times. Now this sounds kind of crazy, right? But actually, if we think about it, we're looking for rows that are not equal to each other. So actually, we expect our result sets to be rather large. There's going to be a lot of rows where the values are not the same. So this can actually make a lot of sense, or it does make sense in this scenario. So I will walk. You're going to stop guessing. Yeah, fair enough. So I will kind of go back. I'll go back to the slides and just kind of show some examples of how these work in practice, or the concepts of how this works. I'll work with just two kind of slightly cut down decks of cards. So we've got 6 on the left here and 6 on the right. So our left cards here are the outer or driving table. So this is the one we're going to start the join with, these cards over on the left, and then we're going to join those to the ones over on the right. So I see there's a couple of things written or something in the question and answer from Suleiman. Jason query. I'm not planning on covering Jason particularly in this session. If we've got time at the end and you've got a specific question about it, then I might be able to address that, but I don't have plans to cover it. We'll see if we've got time at the end. Okay, so we can come back to that if you've got something specific you want to know. Okie dokie. So we have our different, we've got our two data sets and we want to join them together. So let's start off with using a hash join to combine the rows. So what this does is it builds a hash table on the join columns. So we walk through the rows in the first data set, and for each one on the values in the join columns, we build a hash table. So we do that hash and we'll build this little table in the middle. So we start with the queen of arrows there, and that will map to some value. So the thing about a hash function, it's a nice fast operation to map values to an array or a data set like this. I'm not going to go into the details of how hash functions work exactly, but if you want to know more, I'll add some links afterwards. So we're going to go through, and for each of the rows in this first table, I'm going to apply this hash function. So we're going to go through and start mapping values into this hash table like that. Key thing to note here is I will do this for every single card in the first table before we start reading the cards in the second table over here. So we've read the entire of the first data set. We then start walking through the second data set and probing or looking up the values in the hash table. So we apply that same hash function to the join columns. So, value and suit. So we do a hash of queen of arrows, and that will map to the same location as the one from the left, the outer table. There is an entry in the hash table for that, so we have a joined row. That is going to appear in our result set. We've done that hash. We can now walk to the second card in the data set over on our inner data set, the 4 of clouds. So we'll hash that, and that will map to some value which is empty. So there's nothing in the hash table for that value because it doesn't exist in our data set on the left. So that's not going to appear in our data set. That doesn't have a join in this kind data set. So we can ignore that, and we'll go through and do that for the oracle of arrows and so on and so forth. So for each card here, we will apply the same hash function to look for matching rows. So at the end, we've done something a bit like this. We've got our 3 rows which have the same match on suit and value, the oracle of databases, the queen of arrows, and the 7 of clouds. So that's the principle of a hash join. Walk through all the rows in the outer driving data set, build the hash table, then start walking through the rows in the inner data set, checking to see if that value exists in the hash table you just built. So this is nice and efficient if we are reading all the rows in at least one of the tables, but probably both of them, or expect to join most or all the rows in both tables. Because we read all of this first, then go over to the second one. Questions, comments at this point on hash joins and how they work? So that's our hash function. Let's work next to a merge join. And this is sometimes also referred to as a sort merge join, because this sorts the data sets first. So we've got our 2 things. Tables, we want to join them on suit and value again. With our merge join or sort merge join, the first thing it does is sort the rows on the join columns. So we'll sort, in this case, we'll sort first by suit and then by value. So suit alphabetically, so we have arrows at the top. So our 5 of arrows at the bottom on the left here actually is going to be the first in results. So that's going to go all the way to the top, and the 7 of clouds also needs to sort up in the table. And once we've done that, so once we've sorted them, we'll end up with them in this order. We then need to do the same thing with the rows over on the right here on our inner table. We also need to sort those by suit and then value. So let's just rearrange those and sort them like that. So now we've got them sorted, we can actually do the join. And what we can do is start walking through the data sets. So we'll start with the outer left driving table. That's the 5 of arrows. And we'll start looking for matching values over in the right table. So we say, is the 5 of arrows equal to the queen of arrows? No. And the queen of arrows, the value is greater than the 5 of arrows. So queen is greater than 5. We know, therefore, there cannot be another 5 of arrows anywhere else in this inner data set. So we can just stop. We can stop and say there is definitely no matching row for this first value. So we can stop what we're doing. Move to the next card in the outer data set, the queen of arrows. So we'll check that, compare that to first one in the inner data set. That's the queen of arrows. There we go. Bingo, we got a match. Go down to the next card, the next row in the inner data set, oracle of arrows. That is now greater than queen. Ace is the highest valued card, usually. Sometimes it's lowest, but generally ace is the highest valued card. So this is greater. We know there cannot be another queen of arrows anywhere else in this inner data set. So we can stop and go to the third card in our outer data set, the 7 of clouds. So we use the 7 of clouds. Now at this point, we'll actually resume searching from the last value that we had a join on. That is the queen of arrows. So we'll go up to the queen of arrows, that doesn't join, go to the oracle of arrows and so on, and we'll keep going down till eventually we get down to the 7 of clouds. Hey, at last we've got a join. So those match each other. We then need to see if there's any other 7 of clouds in this data set. Go to the next one, oracle of databases. That is greater than 7 of clouds. So there are no other 7 of clouds here. So we can stop. And we've got our matching row. And we'll do that, keep walking down these data sets bit by bit like this. So we'll go to the 4th card here. That's the 2 of databases. Resume searching from our last joined value, 7 of clouds, and repeat the process. So eventually we end up with just our 3 joined values like this. The key thing here is we first sort the data sets, but once we've done that, we just kind of walk down them bit by bit, looking for the matching values. So the actual process of doing the join is very efficient once we've sorted the data, right? But sorting is slow. So it's actually pretty rare you see a merge join because of the sorting overheads there. So what about the, our less than query? So why did that use our sort merge join? Well, let's just simplify a bit here. Let's just compare on value here. So we're saying we want all the cards from the left here which have a greater value than the ones on the right. So now we need to sort the data sets, this time on value. So this one on the left will end up with 2 first, then 3, and so on. So we'll sort like that and sort the other one here. Once we've sorted them, we can then start walking down them. So we start with the 2 of databases, check that against the 4. 2 is less than 4. That doesn't satisfy the join. We ignore it. Then we can go to the 3 and go check again. Is that greater than 4? Nope, it's less. So there cannot be another matching value for it. We can then go to the 5 of arrows. 5 is greater than 4, and at last we have a value that satisfies the join criteria. So that's going to be in our result set. We then compare the 5 to the 7. Well, 5 is less than 7, so we know there can be no other cards on the right here which have a value which are going to be less than 5. So we can stop again. So we're going to keep doing this. We'll then go to the 7, and that will start again from the 4, because we need to start at the top of our data set here, our match value, because these are all potentially less than this value. Check that against 7, we can stop, go to the queen, and that will join the 4 and the 7, go to the oracle, that will join 4, 7, queen, and king. So the thing to notice here is these the smallest value rows in our right data set actually appear in the result set many times. This 4 is, we're getting 4 times in the results. So we're kind of getting a multiplying factor for these potentially. And because we're looking for things that are, less than or greater than, depending which way around you describe it, because these are sorted, we know we can just keep walking down until we find a value which is equal to, and then stop processing. So although we have that little sorting overhead, actually this is quite efficient when we are looking for range criteria like this. Okay, so if you've got any questions on this, please put them in the chat. I noticed there's a comment here from Dennis. So sometimes, actually very often, hash of 2 different values is the same, So two different values are put in the same bucket. And it's not enough just to check that the bucket value on hash join, but we also need to check the values inside the bucket. That's a very good point, Dennis. That kind of gets into a bit of the details of how a hash join, really works. Multiple values can hash to the same bucket. One of the key things driving hash join actually being efficient and worth doing is it being good, in that the chance of two values mapping to the same bucket is relatively low. Not impossible, but relatively low. But it's a good point, Dennis. It's not guaranteed that you're going to get one value in each one. So good addition there. All right then, any comments, questions on the merge join before we move on to nested loop? Nope. Okay. All right. So let's move on to nested loops. All right then. So let's start off again with just doing a nested loop to check that the values and suit are equal. So what a nested loop does is it again starts with the first row in our driving outer data set and looks up the inner data set, starts at the top, or first row in that. Queen of arrows equals queen of arrows. So that's joined, that's in our results. But what it then does is it compares every single other row in the inner data set to the queen of arrows in the outer data set. So this is also then going to be compared to every single other card down here. Right. So we've done that once for queen. We then need to repeat this process for the tour databases. So we've just got a one match row. We'll go to our two tour databases. That also looks at every single row in the inner data set. And the same will happen for the oracle of databases, the three of servers, and so on. Every single row we've got in our outer data set will look up, match every single row over here. That leads to a big explosion in the number of rows we're comparing. Obviously, with just 6 rows in each table here, that's not too big a deal, but even relatively small tables of say 600 rows, that's a lot of comparisons. 6 million, that's completely crazy. So that clearly, when we're checking they're the same, this just really doesn't make any sense to do. But when I was checking for values that were not equal, we did do the nested loop. I was like, well, why is that? Why choose a nested loop? Well, let's see. We're looking for ones where the suit and value are different. They are not the same. So we say, for this queen, we're going to compare it to every single other card here. And notice it will join to, it won't include the queen of arrows, obviously. And it won't include the oracle of arrows either, because the suit is the same. So we can discard those two from our results. But actually, the 4 others all still appear in our results. And if we look at the 2 of databases, that compares to everything. The only one that fails the join is actually the oracle of databases down here. So actually, that includes most of the other rows in the result set. And if we just kind of map on all the other things that are actually going to appear in the results in terms of arrows like this, you see we got a lot of arrows here, a lot of things that are actually joining. And this is generally the case when you're checking when things are not equal to. You're going to get most of the rows in the first set joining to most of the other rows in the other set. Quite often it's pretty close to the Cartesian product. There's relatively few rows we actually discard from the results when doing a not equal comparison. So in this case, using nested loop, checking everything against everything else kind of makes sense, because that's close to what you're going to get in your results anyway. But when we're checking equality, they are the same value. That's the complete opposite. We only expect few rows in our result set. So checking everything against everything else just doesn't make any sense whatsoever. So that was a quick rundown of the 3 join types: nested loop, merge join, hash join. Any other questions or comments on those before we move on and go back to move to a different example? Dennis, doesn't it depend on the data distribution? I mean the anti-join. You mean the example here where they are not equal to? Well, yes. So yes, it does. I mean, for example, if it could be that these all the cards on both sides were all the queen of arrows, in which case nothing would return from a not equal to, and we wasted a lot of effort. But generally speaking, that's relatively rare. Generally speaking, usually, if you've got relative, suit and value are unique in this. Even if we haven't enforced that via unique constraints, the optimizer knows that there are relatively few combinations of each. So a nested loop join makes sense here. So yes, it does depend on the data distribution, and maybe things like if you were comparing on something like currency for finding things which are different currencies. Most businesses will only deal with a handful of different currencies. If you're European, you might have euros, maybe pounds, and some of the NOK and Swedish krona and some of the krona currencies, things like that. But it's relatively few. So actually, not equal to won't return this big multiplication. But if you're comparing things like customer ID on orders, then you hopefully, for most businesses, there's going to be a lot not equal to. So yes, it does depend on the data distribution. Well, all of these joins really depend on the data distribution, but generally speaking, not equal to like this will return a large fraction of the rows. Does that help answer the question, Dennis? Okay, so Fian, what is the order of best performance? So that's a good question, and we'll walk through this in a bit more detail because the answer is that, as always with performance, it depends. So keep that question in mind as we go through this session. We'll discuss some of the things that affect that, and if you're still unsure at the end, then let me know. So Charles, is there a difference in the evaluation of not equal to, as in exclamation equal and greater than, less than, not equal to? Not that I'm aware of, Charles, but I haven't done any extensive testing on that, so I'm not aware of that having any particular difference. Okay, so Dennis, totally agree, but even in common case, isn't it better to first generate the Cartesian product and then filter out the join using a hash join rows? I'm not sure I'm following exactly, Dennis, but I mean, how would you generate that Cartesian product is the answer. I mean, quite often the Cartesian product will be generated by nested loops. You have to do something to combine the data sets. So I'm not sure how you would generate the Cartesian product without doing this. I mean, you might do a merge join, and actually you do see cases where the optimizer expects just one row from this outer table here. It does a merge join Cartesian, but to do the Cartesian product, you've got to join them, right? So I'm not really following what you're trying to get to there. Okay, any other questions or comments before we move on? No? Okay, maybe. All right. All right then, so let's look at a common type of query you might want to run, a top-end query. So far in the previous examples, what we did is joined every row. Well, stick with equality, because to be honest, vast majority of joins you write will have at least one column equal to at least one column in the other table. Not always, but it's very rare that you don't have at least one equality in them. So let's just stick with the simple equalities for now on. So let's say we're going to do a top n, and I'm doing, say, a random top n because I have got no order by. So this is just going to return me the first 5 rows from that satisfy the join. So let's have another vote here. How do we think this is going to join these tables? Nested loop, hash join, merge join. We are going to get the first 5 rows that have the same value in suit, which in this case means we read just 5 rows from each table. Who's going to vote nested loop? Who's going to vote hash join, merge join? Bet for nested loops. Any other takers? Okay, let's merge from Neil. Okay. people not quite sure around this. It's a bit trickier, this one, isn't it? It's a bit trickier because it's, so yeah, so Dennis, hash. Oh, we've got, oh, nice split, everyone going for something. All right then, so let's see what happens. There we go. So let's run this, and it will take a second or so to come up, and oh, it's still hidden. We've got nested loops. So why has it gone with nested loops? Well, as Dennis predicted, because it's only 5. So for nested loop, for each row we get from this first table, we're going to do a lookup on this second table. And in this case, it means we can read just 5 rows from this first table. So one of the big differences between a nested loop and a hash or a merge join is a nested loop, as soon as it reads that first row, it can start looking up rows on the inner table. Hash join, on the other hand, still has to read all the rows in the first data set. So it's still got to build that hash table on the first data set before it even looks at the second data set. Similarly, merge join has to sort the 2 data sets before it can start comparing them. Nested loop, on the other hand, looks at that first row and can straight away do a lookup on the inner table. And in this case, the optimizer kind of thinks that's going to be nice and efficient, or it's going to be faster to do. But, you know, it's chosen this, but is it really efficient? Well, it means we're doing, 5 full scans of that inner table. So what it's decided to do, is that really best? Yeah, okay, maybe not. But this is just getting any 5 rows. To be honest, other than, testing things out or trying to generate some test data or sample data or something like that, hopefully you're never writing a query like this, right? Hopefully all your queries would actually have an order by in there, right? So pretty unusual we'd write that original query. So let's try a top n again, but this time we will sort the data. We're going to sort it on one of the join columns, the card value. So top n, we're going to get just 5 rows in our result set, but we've sorted it by value. So which join type do we expect this time? Let's have another vote. Hash join, merge for helium, hash. Any other takers for anything else? No. Mesh. You just hedging your bets there, Neil, with that, or is it a typo? A mix of the 3, right? Hash, I believe. Okay, once again, we've got some split votes here, so that's good. All right, so let's see what actually happens. So we'll run this, and and let's bring it up, and then ping this down. So we find we've got our select and hash join. Okay, so what's the big difference? Why has it chosen a hash join as opposed to a nested loop in this example? Well, the key thing is it has to join the rows and then sort them, okay? Because, I mean, okay, this is a bit of a daft example. You're joining the same table to itself. But in the general case, we don't really know that for every row in this first table, we'll actually get a matching row in the second table. This is a bit of a toy, silly example, but in the real world, when you're joining different tables, the optimizer doesn't know that they're all going to match, and it needs to join the rows first and then sort them. Then, and only once it's sorted the joined result set, can it get the first 5. Because it could be that actually, after we've done the join, we have no rows, possibly. Or it could be we have 5 million rows. We don't know in the general case. But we do know which ones Tosrot, do we? Do ones which to sort, right? So this is an interesting question, and actually, there is perhaps an argument that maybe it should have gone with the merge join in this case. So yeah, so we know we're joining on value, and we know we're sorting by that. So maybe we should have done that sort in this case. And I can see why you would think that, and actually, it's kind of, one of those probably little balancing point edge cases. I think the key thing here is a hash join will read each data set once. So it will read the inner data set, the outer data set, read the inner data set, do the join, and then sort them. hoping that probably that sort join will knock out some rows, whereas the merge join has to do the sorting first of both data sets. So with the merge join, we've still got 2 sorts, whereas the hash join, we've only got 1 sort, which may even sort less data. It might sort more, depends on data distribution. So there's a hash of each row used in the sort or the actual rows. To sort the data set, it's using the value. I'm not sure I'm following your question exactly. So it sorts based on the values here. And then, excuse me, are you asking, is it sorting the entire row or is it sorting just the values? Is that what your question is? Okay, well, I meant the value. So basically, it joins these 2 data sets, and once it's got those, it sorts it by whatever that value is. So if we just, and then returns the first 5. So we get rid of the top end bit of it. It's joined these 2. So it's found ones where, the ace of hearts join to the ace of hearts, unsurprisingly. Then it's sorting by this column here. So it's basically done that and then this, just internally. So you see how I got the join rows and sorted them just by doing the SQL developer clicky thing. That's essentially what it's done, but just all internally. So it does join and then sort. Is that answering your question? I'm not sure that's exactly what you're looking for. So yes, you're sorting on the actual values. You're not sorting on a hash of the value, you're sorting on the actual value. You can't sort on the hash of the values because that hash value could be anything. It's, that's the point of the hash function is you kind of could map to any value and you don't really care what that intermediate value is. I mean, we as end users don't care what it is. I mean, the optimizer just uses that as an efficient way to compare the rows. You are definitely, when you've got your order by, you are sorting on whatever the actual value is here. So that, card value. You're wondering why 10 is top. It's because it's sorting alphabetically rather than numerically. So 10, the string, what characters 10 is less than the character 2. If you're wondering why that's top. So it sorts on the value, not the hash of the value. Okay. Okay. All right then. So far we've been doing our top n, but everything has had no indexes, completely unindexed joins. That's again kind of unrealistic. Usually there'll be at least a few indexes in your database. So let's see what happens when we create an index on the join columns. So we're joining on suit and value, and we've got our index on that. And we are going to do our top n on that, sorting by the first column in the index. So what do we think we're going to do here? So what do we think? Nested loop, hash join, merge join. Vote for same query as before, but this time we've got an index on the join columns. While you're typing your suggestion, and let's see, comment from Judith. Okay, but it could be a case for nested loops if the optimizer knows something of the selectivity of the join. For a high selectivity, it can get the first 5 rows much faster. I'm not sure exactly what you're getting at there. When you say, what you're getting at there, Judith, when you say nested loops for the optimizer knows something of selectivity. If you could expand on that, but okay, we've got a suggestion from Dennis that we've got sort merge. Any other takers? Nested loop index lookup from David. What are the guesses or estimates, predictions? So joining on value and suit, sorting by value, get the first 5 rows. All right, you've had a minute to think about that, so let's run the query anyway. So here we go. So let's get the execution plan, and when it's come up, let's drop that down. We find nested loops. Aha. So why nested loops? Well, First thing to note is, as you're kind of saying, Dennis, we've got the index to read the values from the sort there. So we can actually use that to read the values from our outer table and get the values in the order that we want them, and then start doing our index lookups of the inner table. But for each row we get from this outer table, from the index lookup, we're going to get one row on the inner table. So we've got 5 index lookups, so last starts 5 over here, of our inner table. So instead of 5 full scans of the table, we've got 5 index lookups. Much bigger saving. So now it is possible that sort merge might be more efficient in this case, and it's probably one of those where in some data sets the exact values will tip it towards a sort merge. But one of the things is the index saves the sort on the out of the driving data set, but in Oracle database, it still sorts the inner data set. So even though we've got an index on those columns in the order, we can read them out the index in the order we want, it still won't use that. It'll still actually do a sort. So we've still saved ourselves a sort with index lookup, looking at just those 5 rows. So that's probably the key thing driving it to a nested loop in this case. Getting fast to the first, this is almost what I meant before, getting fast to the first 5 rows. All right. Okay, so, all right, I think you're jumping ahead of where we're going then, Judith. I think if you know, probably getting too far out of where we actually are. Fair enough. Okay, so by creating that index, the nested loop went from doing 5 potentially really slow merge join full scans to 5 hopefully pretty quick index lookups. So let's jump back over to our slides at this point. There we go, bring those up. So let's run through those kind of quickly. So start off with, we wanted to do any top n. So this is where we weren't sorting, we were just getting few rows. So in this case, smaller data set, I'll just join on suits, just keep things a bit simpler and get 3 rows in the results. So first thing we'll do with our hash join, we'll run through all the cards in the outer data set, hash them on suit. So queen goes to this, databases go to that. And at this point, notice, because we're hashing on just one value and some multiple cards have the same value, we get multiple rows in each bucket. It's not quite the same as Dennis was describing earlier, but in general, you could have multiple rows in a bucket, if the values you're joining on are not unique. Still possible, different values could hash to the same bucket, but that's a slightly different thing. So we've read all the rows here. We've read them all, and we had to read all of them before we can start reading our inner table. So we'll do the same now. Apply the hash function to our suit. Start with a queen of arrows. That will hash to this first bucket here. There's 2 rows with the same suit, so we've already got 2 rows in our result set. We'll then go to the next card, the 4 of clouds, hash that to the 7 of clouds. That matches on suit. And now we've got all the 3 rows we want. So we can stop. So we read all the rows in our outer left data set and just 2 rows from our inner data set. Exactly how many we'll have to read will obviously vary depending on how likely it is we are to actually join. But the key point is we can stop processing once we've found our first n rows. So nested loop, on the other hand, well, we start with our queen and we're joining just on suit. And again, that will compare to every single row in the inner data set. So we get 1 full scan of this inner data set and we've got 2 matching rows. We then go to our databases, to our databases, compares to every single one, gets down to the Oracle of databases. So we now have our 3rd matching row. We've got our 3 rows in our result set. Stop. We don't need to do 3 full scans of this data set here. And this can make the performance of this nested loop quite unpredictable, actually, because we could be really lucky, and there actually is 4 or 5 cards from the arrow suit over here, in which case we can have just 1 full scan. There could be none, or maybe all the cards are clouds or something like that. in which case we might have to do 3, 4, or 5 full scans of this table. Performance in this is going to be quite variable depending on exactly which cards and potentially even which order we read the cards out of this first table. Not particularly good in this scenario. But when we create the index on the suit over here, we can then start again with our outer table, the Queen of Arrows, look up the index, go to the arrows entries, and find the Queen and the Oracle over there. So we got our 2 rows. We then go to the next cards, the 2 of databases. That will search the index for the database entries and go over to the Oracle database. Stop. We've done 3 index lookups of this inner table and read just 2 rows from the outer table. Compare that to the hash join. Hash join read the entirety of that first data set, whereas the nested loop read just the first 2 rows. And unlike the nested loops, hash join cannot take advantage of this index on the inner table. Okay, so the fact we've got an index here does not help the hash join, but it makes a massive, massive difference to the index lookups. So that's when we're fetching any 3 random rows. We read just 2 rows from the outer table and the 3 matching rows on the inner table in this example, plus look up the index. Pretty efficient. Okay, so that's pretty unusual, a random top n. Let's do a sorted top n. Now the key thing here is the order is we join, sort, and then we limit, right? So to sort, we have to read all the rows, right? Why? Well, of course, the last row we read might have the smallest value. So we still need to join everything, sort it, then limit it, which implies that either a hash or a merge join is going to be best. Unless, as we saw, we create an index on this outer table. So we create an index on suit here, start by reading the index, go to the first index entry, the arrows, and that will be the Queen of Arrows. Use that to find the matching cards there, then use the index again over here to find the 5 of arrows and look it up, and that will match to either the Queen or Oracle of Arrows, depending on which ones it finds first. So by creating this index on the outer, the driving table, the nested loop can read the rows in index order from it, saving ourselves a sort, and just look up the matching rows on this inner table. We could also potentially use this to do a merge join here. This index could allow the merge join to avoid a sort, but it would still have to sort this inner data set. So it still has to read the entire thing. With the index lookup, we're just getting 3 rows or however many it is that actually match. Okay. Questions, comments on that before we move on? Which makes this nested loops join look like sort merge when we have indexes. But yeah, it does a little bit make it look like a sort merge. You're right, Dennis, because we've used the index to do the sorting. The fact the indexes are ordered data structures, so we don't have to sort the data. We just read the index. So it does look, you're right, it does look a bit like a sort merge, but we've saved ourselves a sort, basically. Any other questions or comments? I notice time seems to be whizzing by today. We've still got a couple of other things I want to mention. So let's very quickly jump. Well, no, stick with that. So keep typing if you want to go, but one other thing I want to mention before we wrap up. So far we've been joining basically everything, or a top n, getting everything. Usually you want to filter data sets first. So let's jump back over here. Let's get rid of these and do a query that looks a little bit like this. Bit like this. You've got a where clause filtering one of the tables. So this returns us just 1 row. And we are getting a bit short of time, so I'll just go ahead and do this. Actually, no, let's have one less try. What do we guess? Nested loop or hash join? What do we think this is going to be to join these tables? Nested loop. Any other takers? Nested loop? Oh, quite a few going for nested loop. Any hash? Dennis going hash. So this is an interesting question, because which one we should use actually depends a lot on how many rows have this damaged property. If it's just one, we probably want to use a nested loop. But if there's loads, we probably want to do a hash join. So what does the optimizer do? Well, it hedges its bets. It does both, or it considers both. So this is an optimization which came in 12C, adaptive plans. And it's one plan that considers two join types. And the key thing is, if we do get just one row here, then yeah, we want to use a nested loop. But what if there's more? What if the stats are out of date slightly, or it's one of those situations the optimizer can't get the stats right? Well, we want to use a hash join. This is tricky because there's lots of reasons, valid reasons, and some bad reasons as well. These estimates could be wrong. So the optimizer can end up out of sync here. So with adaptive plans, it hedges its bets and it chooses both. You can spot this with this statistics collector step here. And what that means is, if I go through and let me just save that. Now, how do we know which join type it actually did? Look for this last start here. We did not do this full scan at the bottom, which means we didn't do the hash join. And you can also get the plan a different way. I'll show you in a sec. So we save that. We will regather stats on the table. Do that a couple of times. This time we're getting lots of rows from that outer table. So hopefully this has all gone to plan. It's still an adaptive plan, but this time, yeah. See these last starts for these index lookups? It's gone. It's chosen the hash join because that is more efficient. So it's hedged its bets and said, what's going to happen here? And the key thing is, it doesn't necessarily know. So it goes, well, I'll consider both, and on first execution, choose one. So once we've done that first execution, it's kind of locked into that plan unless something forces it to change, such as regathering stats or adaptive cursor sharing, or one of the various other things which invalidate queries. So I'll just very quickly run through adaptive plans, what we do. So you see something a bit scary that looks like this. Key thing to look for is this statistics collector step. That is watching the rows coming out of this full scan and saying, is this less than some threshold? So that's a cost-based decision depending on your query. Yes, do nested loop. No, do a hash join. So as long as the rows coming into this, it kind of buffers the rows, stays below a threshold, it does this, and it will walk through the data set kind of like that, do a nested loop. If it goes above it, it will switch instead to a hash join and do something like that. And it does that on the first execution of the query. If you want the actual plan, you can use dbms xplan, and it will give it to you without it'll say this is adaptive, but it won't give you the extra gubbins. If you want to see the adaptive information, add the plus adaptive there. So Dennis, is it a 19C EE feature? No, it is a 12C feature, and I believe it's all editions as well. I don't think it's limited to EE, but I'd have to check that. But it's a 12C feature. It's been around for a long time, this. Okay, we're getting towards the end. I'm happy to hang around for questions, but I understand some of you might need to rush off. So I will just recap for a bit, and if you want to hang around and ask questions, then feel free to do so. So very quickly, you're stuck in an 11G, unfortunately, Dennis. Oh, sorry for you. All right then. So we looked at our join types and just mentioned which is more efficient, or time complexity, the big O notation, which some of you may be familiar with if you've ever done computer science. Key thing to notice here is, so we're saying number of rows from T1 plus the number of rows from T2 for our hash join. That's the amount of work we're doing. This is the least. Merge join, on the other hand, multiplies the number of rows roughly by the log of the number of rows as well. So clearly this is bigger than that, so slower. That's coming from the sorting, basically. Nested loop is the multiple of the two. It's like, so clearly nested loop here is by far and away the slowest. So, you know, why does it ever choose anything other than the hash join? Well, hash joins in Oracle database at least have to have an equality. You have to check that columns from one table equal columns from another table. Otherwise, the database won't choose a hash join. The other thing is, hash join cannot take advantage of an index on the join columns. Merge join it can save itself a sort of the outer table, which can reduce the work here. But critically, with nested loops, it is able to look up the inner table. So a hash join will still have to read all of the rows out of the first table. Let's imagine you're joining a 1,000,000-row table and you're expecting just 10 rows in your results. You've hashed a whole million of them, then started reading your second data set to find the 10 matching rows. Nested loops can find, start reading the first row, do the index lookup, get one matching row. So nested loop may only need to read 10 rows from each table. So this is the key difference, key benefit of a nested loop. And if we were going back to your question, if someone was asking earlier about performance, which is faster, I say it depends. It depends on what indexes you have available, what fraction of the data set you're joining, and so on. So a hash join is best when you are joining all the rows in one or both data sets, usually both, or large data sets in general. A merge join is best if the data sets are already sorted, but this is pretty unusual and sorting is slow. So if the data sets are sorted for some reason, merge join is perfect, but the rest of the time it tends not to happen. A nested loop is best when joining a small fraction of the rows. And this is usually the most common type of join. Get the order, look up the matching order lines, get the customer, find their matching orders, find all the orders placed today and the invoices associated with them, that kind of thing. So nested loop tends to be very common when you're joining tiny data sets. So that's what I wanted to cover. As I said, we're just past the hour. So if you want to ask more questions, I'm happy to stick around. But otherwise, thank you all for joining me. Hope you enjoyed this. More importantly, I hope you learned something and hope to see you again next month. Thank you.